So in this video, we are going to be discussing continuous versus discrete graphs. So first we need to kind of start talking about the different kinds of situations that graphs can actually help you understand things a little bit better. So graphs are really important for visualizing data. So one example of this is cardiographs that can help doctors actually see how your heart is moving. So they are running electrical pulses through your heart to actually see how fast it's beating, how it's beating, all kinds of cool things that they can see based off of that. And they're looking at the graph to see any kind of fluctuations instead of looking at the hard data, the numbers. So graphs can actually help us quickly understand a situation. So one thing that's going to be extremely helpful moving forward is always pay attention to what the labels of each axis represent. So the x-axis and the y-axis will always have some kind of label. So typically the x-axis is time, so it will be some function of time, and the y-axis could be literally anything. Just pay close attention to how they are labeled, and always make sure when you are writing a graph that you label your axis. So an example. So here, before I even read this example, I'm going to go ahead and I'm going to look at my x and y axis. So I can see that my x-axis is talking about time. So that means as I'm moving left to right, some amount of time is passing. So it could be days, it could be weeks, it could be months, it could be seconds, but whatever it is, from left to right, time is moving forward. So on my y-axis, we have leaves. So it's telling me that if I move up and down in this graph, it tells me how many leaves are whatever it may be in the question. So this is representing the amount of leaves. So that means if we're going up, that means we're increasing the amount of leaves. If we're moving down on this y-axis, we would be decreasing the number of leaves. So let's read this question. So it says, each day several leaves are falling from a tree. One day a gust of wind blows off many leaves. Eventually there are no more leaves on the tree. Okay, so let's kind of break this kind of down so we can see what's going on. So it says each day, so that means as time is moving forward, we have leaves falling. So that means that we are decreasing the amount of leaves on this tree. So then it says one day a gust of wind blows off many leaves. So that means maybe we're looking at a large decrease. So something that isn't happening normally. So usually we're losing like 5 leaves a day, then all of a sudden because of the wind we just lost like 15 leaves in that day. So eventually there are no more leaves on the tree. So based off of this right here, that there's no more leaves, I need to make sure that my graph goes to 0. So at some point I should have a y equals 0. And what that means is that I hit the x-axis. So looking at that last statement, so I'm going to put this in blue. So that means that I should see on every single one of these graphs that I eventually end with no more leaves. So all 3 of these graphs work in that case. Now, the fact that we're decreasing every day, well, that didn't really show up that well, shows me that this piece right here doesn't make sense. My tree isn't growing any more leaves, they're losing the leaves. So I know that this one cannot be the right answer because somehow eventually I increased in my leaves. So looking at these other 2 graphs, I have points where I'm constantly decreasing. So I'm going down the amount of leaves as time moves forward. So here, we can kind of see that that's happening. Same with over here. But here we have this weird constant thing happening. So anytime I have this constant flat surface, it means that there's no change. So what that no change is looking like, it's meaning that the tree doesn't lose any leaves during that amount of time. And that doesn't say that anywhere in this sentence. It says actually that we lose more leaves from the wind. And that's what this is representing right here, that we have a sharper decline. So my slope is steeper, which means that I'm losing things quicker. So the amount of time is shorter and the amount of leaves is more. So I'm losing more leaves in a shorter amount of time. So that could represent the wind. So graph B makes the most sense here. All right, so you guys give it a try, see if you can understand what this is asking for. So make sure you read your X and Y axis and then read through this and kind of get a picture of what's going on in this situation. And then come back and check your answer. All right, so on this one, you should have had graph C. So graph C shows that you have the steady increase and then a period where you're constant. Then you see another increase followed by a sharp decrease. All right, let's keep on moving on. So with these graphs, we have two different types. We have what's called continuous graphs and we have what's called discrete graphs. So both of these, continuous and discrete, are their own separate categories of math. So if you go on to higher level math, there is stuff called discrete algebra, or you have discrete calculus or continuous calculus. So it just depends on what it's actually talking about. So these connected lines, so meaning that we have a continuous source of information, these are going to be our continuous graphs. So we're looking for these connected lines. So we care about lines being connected, meaning that we could connect the lines. And discrete graphs are only going to be points. So points on a graph that you can't connect. And there's a reason why we can't connect them. So let's look at this example and really understand why this one is discrete and why we could never actually connect these lines. So here we have an example of a theme park attendance. My y-axis is the amount of people we have, and the x-axis is the amount of years. So again, there's our time. So that means as years are moving on, we can see that the amount of people that are going to this park is decreasing. So the fact that these points are not connected is telling us that this is a discrete graph. So this is discrete. So, and it's because it's only points. So if you think about it, why can't we connect those lines? Why doesn't it make sense that we can't connect these lines and make this graph look something like this? Well, the reason behind that, if I zoomed in really, I can't, oh yeah, we can zoom in a little bit more. Nope, that's as much as I can zoom in. Basically, I'm saying since I've connected these points that this line is true as well, which means that I can take a point from this line and say, hey, at some point, we could say at year 2019.57, we had 39.425 people. And that makes no sense. We cannot have 0.425 amount of people. So because we can't have these fractions of people, it doesn't allow us to connect these dots, because a line means that every point on that line is a solution. But I can't go around and saying, hey, do you guys remember in year 2020.592374 where we only had, or I don't even know what a good example for people would be. But again, we just can't have these fractions of people. It can kind of make sense for fractions of years because years is a time kind of thing. So we could still pinpoint where that time point was within that year, but we can't go and say a fraction of a person. So it's because of that fraction of a person we cannot connect these lines. So no connection. So that's going to be very important. So when you are trying to decide on whether or not something is continuous or discrete, always ask yourself, can I take a fraction of whatever I am looking at? Could I have a fraction of a person? Would I want to sell a fraction of a hamburger to someone? No. I don't who would want to go and buy 0.005 of a hamburger? That makes no sense. That's like maybe you get a sesame seed. So we talk in wholes for a lot of things. So the fact that they're whole means that it's going to be discrete. So we don't have the ability to go from one point to another point. Now, if it was continuous, meaning that we could look at every single point on that line, no matter where it is, that's going to be the continuous. And we'll see some examples of that. So, looking here, it says we want to sketch a graph and tell whether the graph is going to be continuous or discrete. So we have a truck driver who enters a street, drives at a constant speed, stops at a light, and then continues. So first I need to come up with a x and y axis. So again, one of the best x-axis titles would be your time. So we have time here because if you think about it, as time is moving on, all of these things are happening to this truck driver. So we want to put our time as our x-axis whenever possible. Our y-axis, if we look at it, they're talking about some kind of speed. So I'm going to put speed as my y-axis. So if I think about it, just from those two labels, does it make sense to have fractions of time? Yeah. If you look at stopwatches all the time, you have decimals. Does it make sense to have fractions of speed? Yeah, I'm not going to be able to jump from 15 to 30 miles per hour without increasing my speed steadily. So both of these things are continuous, so I know that this is going to be a continuous graph to start with, which means I can draw straight lines instead of points. So first, let's start with the first piece of information. So it said at the beginning, a truck driver enters into a street. So let's think about what his starting speed might be, and as he's entering into a street, should he slow down? Should he speed up? Should he remain at the constant speed? So most of you aren't drivers yet, but you will eventually be. Typically, when you enter a street, at some point you have stopped first or have gotten a low enough speed before making that turn. So I'm going to just say that at the beginning he has stopped. So he is at a stop sign and he's about to turn into the street. So I'm going to say that at the beginning I have 0 speed and 0 time because that is the beginning. So he enters a street. So it doesn't make sense for him to, if he's entering a street, it doesn't make sense for him to remain at a 0 speed. That would mean he's not moving. So that means we're increasing our speed. So as he's entering, he's increasing his speed. So mine was a little bit curved because if you think about it, at the beginning you're slowly making that turn and then you're hitting that gas pedal to speed up. So mine was a little bit curved. It's okay in the beginning to have a straight line there. So then he drives at a constant speed. So a constant speed means his speed is not increasing or decreasing. So that means that once he gets to some desired speed, he's gonna like flatten out. So I should see a horizontal line there because that's saying no matter what time I'm looking at, that speed is the exact same. So then he's going to stop at a light. So for him to be able to stop, he needs to slow down first. So he doesn't immediately go down to zero. If he went down to zero from some speed, that means he crashed. So we're going to be decreasing until we hit zero, which means that he's stopped. He's no longer moving. He has a speed of zero. And then we wait some time because he's at a light, so who knows how long that light takes. So he's going to remain at zero for a while, and then he's going to continue on this speed. So he's going to again ramp back up to some speed and then level it out. So this is how I would draw this picture. So again, we started at zero because he was entering into a street. He increased his speed to get to the speed limit. Then when he hit that speed limit, he remains at a constant speed. So he's, let's say the road was 35, he's remaining at 35 that whole time. For him to be able to stop at a light, he has to slow down before he gets to a complete stop. So again, I should see a decreasing line. Then he's going to stay there for a little bit because it's a light and he has to wait for it to change back to green. Then we see this exact same beginning again where we have the increase and then a constant speed. So let's look at this one. So again, we're going to sketch a graph and figure out if it's continuous or discrete. So it says a small bookstore sold between 5 and 8 books each day for 7 days. All right. So I know that for my X and Y axis, again, time is a good XY or X axis, and we're talking about days here. So days are a type of time. And then the Y axis would be how many books are sold. So I'm going to put the number of books sold. So for those of you that may not know, this isn't a hashtag, this is a pound symbol, and the pound symbol also refers to the number of, so the amount. So typically in shorthand notation, if you see a pound symbol when talking about the amount of something, that's what it represents. It doesn't mean hashtag books sold, this isn't Twitter. So that's just the shorthand, and you will see me use that all the time when talking about the amount. All right, so let's think about this. So as of right now, before even graphing anything, just based off of those X and Y axis, I could already tell whether or not this should be discrete or continuous. The fact we're talking about days, it kind of makes sense to have half a day. We say things like that. Half a day would be noon. But can you sell half of a book? Could you sell a quarter of a book? No. So just because of the fact that we can't sell half of books, this is going to be discrete, which means we're just going to be plotting points. So instead of lines, we're going to be plotting points. So since we have some specifics here, so we have 7 days, so I'm going to have little 7 hashes. 1, 2, 3, 4, 5, 6, 7, and our books sold need to be between 5 and 8. So we don't have any more information, so we kind of get to make it up. So as long as each day that I have, I'm somewhere, my point is between 5 and 8, that's good. So let's say on the first day we sold 8 books. So I'm going to come up here to 1, 8, and there's my books sold. On the second day, let's say we did 6 books, then 7 books, then 5 books, then 5 books again. then 8 books. Then let's say 6. So this right here allows us to see how many books we sold each day. So again, it's discrete because it doesn't make sense for me to connect those dots. I can't have half of a book sold. That doesn't make sense. So let's do the opposite. Let's say that we are given a graph and we want to come up with some kind of scenario. So here we have our y-axis being speed. So that means if it goes up, it's increasing our speed. So that means instead of going 50 miles an hour, we would go 60 miles an hour. Anything going down would mean we're decreasing. And our x-axis is time, so that means as time is moving forward, we're either going to increase or decrease, and we need to come up with some kind of scenario here. So looking at this first part, I see that I'm starting at some high speed and then I decrease my speed. So thinking of a scenario where I'm starting at a speed and I need to decrease it to the point where I start to go to a constant speed. So that means that my speed doesn't change. So I went from going some amount of speed to slowing down and then remaining at some speed. So we can go and put some random numbers here. Let's say that this was 80 miles per hour. And then when we get to down here, we're going like 50 miles per hour. So again, this constant line right here is still some amount of speed because it's somewhere on this y-axis. So it's not 0. So we haven't stopped. We're just going at a constant speed, and that constant speed is just 50 miles an hour. So then again, we then slowly decrease again to the point where we do come to a stopping point where I'm going 0 miles per hour because I've hit the x-axis, which means I've stopped. I'm not moving anymore. So we can come up with the scenario. I can think of one. So let's say that you are driving and you are speeding, and then all of a sudden you see a cop. So because you see that cop, you decide to slow down to the speed limit. So you remain at that speed limit until that cop comes behind you, turns on their lights, and tells you, well, it's time for you to pull over because you were speeding. So you slow all the way down and you stop. So that's what I see there. There could be all kinds of other things. So again, we're talking about speed here. So we're not moving up or down any kinds of hills. We're not talking about distance. We're talking about how fast we're going in relationships to time. So be aware of what that means for your y and your x-axis at any given point. So here are 2 U-tries for you guys to do. So the first one, you are making a graph and telling whether it's continuous or discrete. And the second one, you're going to try to come up with some scenario that makes sense for it. All right. So on the first one, your x-axis should have been time. Your y-axis, you kind of have a choice here on how you want to think about it. It could be the amount of water in the tank, which is what I did. It could have also been the amount of water out of the tank. So that would have just looked a little bit different. It basically would have been flipped everything. So I did mine in the water out of the tank just because I want to know when there's no more water in the tank. So that would be when I have hit the x-axis. So you can see that I'm decreasing because there was a single valve open. So when the second valve opens, that means now more water is able to get out. So that means it's speeding up the amount. So you can see that we have a little a sharper decrease here. And then you close off the valve, so then it kind of starts to go back to somewhat the same slope as the first one. So on the second one, you could have said anything that you could think about, like potentially when you got to the fifth student, you needed to buy another pizza. So you can see that through the first, second, third, and fourth student, you only needed to buy one pizza. But then when that fifth student came into the picture, then you needed to at least buy two. And then you were still good with two pizzas for the sixth, seventh, and eighth person.